Good day and welcome back to the fourth part of our discussion on maximum and minimum values. In the previous videos, we've introduced kind of computationally how we define and find critical points of a function of several variables. And in the previous video, we even discussed how we can classify those critical points as local maxes, minimums, or saddle points by making use of something called the second derivative test. And in this video, we're going to look at one more example involving the classification of the critical points. And as we discussed at the end of the previous video, these can certainly be somewhat involved computationally, so it really requires practice to become comfortable and efficient with those standard techniques. And what I would like to ask you all to do at this point is to pause the video and go through the process. First, find the critical points, then use the second derivative test to classify them. Once you've done that, hit play and we'll kind of go through the work and the steps together. Our first step is to find the critical points. That is, calculate the two first partials, and set them equal to 0. So the partial f sub x is going to be equal to 3x squared minus 12y, and f sub y is equal to minus 12x plus 24y squared. And in order to have a critical point, we need to find the values, x and y, our inputs, that would simultaneously make both of these first partials equal to 0. And remember our technique. We pick one equation, we work with it until we have enough information to substitute back into the second equation. And in this case, as both of those equations have similar level of difficulty, we could pick either to start with, and I'll just go ahead and pick the top one. So 3x squared minus 12y equals 0 is equivalent to writing 12y is equal to 3x squared, or y is equal to 1/4 x squared. And that gives us enough information to substitute into the second equation, because that single y we see, we can replace it with that quantity 1/4 x squared. So similar to our work on the previous video, we now have minus 12x plus 24 times the quantity 1/4 x squared squared equals 0. So we took the value of y and we replaced it with 1/4 x squared. And now our job is to algebraically simplify and solve for x. And one thing I'm going to immediately note is that we have this common factor in both terms, an x, but also a 12th. If we wanted to divide each and every term by 12, that 24 would become a 2. So it's simpler, I believe, to write this as minus x plus 2 multiplied by this quantity squared. So 1/4 squared is 1/16. X squared squared is x to the 4th. Now we will go ahead and reorder the terms, so in descending order, so 1/8 x to the 4th minus x is equal to 0. So x, and if we go ahead, and I think it's simpler here to pull out a 1/8 along with it, we would have an x cubed minus 8 left over. And the only way for this product of two quantities to equal 0 is if one or the other is 0. So we could have x is equal to 0, or we could have x cubed minus 8 is 0, which means x cubed is equal to 8, or x is equal to the cube root of 8, which is 2. So very similar to our previous problem, we worked with the first equation until we had enough information to plug into the second equation. The powerful thing is once we get that substituted in, it now only involves a single variable, and here we can algebraically solve for the two possible solutions. And this is going to describe for us what our critical points will be. So in terms of our critical points, they are going to occur when x is equal to 0, or x is equal to 2, with y being 1/4 x squared. And the important step is to remember that y equals 1/4 x squared from the first equation is coming back up and needs to be used. So for our possible values of x, when x is 0, that would imply y is 1/4 times 0 squared, which is 0. So one critical point is 0, 0. Secondly, we could have x is equal to 2, which would imply y is equal to 1/4 times 2 squared, which is 4/4. So our second critical point is 2, 1. And now that we've identified the two critical points, we can classify them using the second derivative test. But for that second derivative test, we need to calculate some of these second partials. That is, we might want f sub xx, f sub yy, and f sub xy. And note f sub xy or f sub yx can be used interchangeably. Looking at our first partials above, f sub xx is 6x, f sub yy is 48y, and f sub xy is minus 12. So the function that we are interested in using, this d of x comma y, remember its formula. It's going to be f sub xx multiplied by f sub yy, and we subtract away f sub xy, that mixed partial, squared. So note those quantities, f sub xx, f sub yy, and in the brackets would be f sub xy. And simplifying it just a smidge, we can note that we have 6 times 48 times x times y minus 144. So at the first critical point of 0, 0, we get back minus 144, which is certainly negative. And that's going to tell us that 0, 0 is a saddle point. And note in our previous example as well, we had a saddle point, but that will not always happen. When we have our critical points and we classify them, it can be any possible combinations of local maxes, minimums, or saddle points. Similar computations for the critical point 2, 1 tells us that we will have 6 times 48 times 2 times 1 minus 144. And I intentionally left this very kind of general and didn't simplify, just to illustrate it doesn't necessarily matter what we have. I just know with certainty that this first part is larger than 144, so that this is a positive quantity. And that means that I'm going to have a local max or a local minimum at 2, 1, depending upon the value of the second partial, f sub xx, or f sub yy, whichever one you prefer. So this would be 6 times 2, which equals 12, and is positive. If that second derivative is positive at a point, we think concave upward, which indicates a local minimum. So these computations imply 2, 1 is a local minimum, which finishes the classification of the critical points. And it's always worth noting kind of what type of work you need to show, and essentially all of the key steps that you see here would need to somehow be included in your work, hopefully in an organized fashion. So you would need to have the first partials equal to 0, solving for them to get the critical points. And then once you have the critical points, you would also have to show those computations that indicate what the second derivative test tells us. In the next video, we'll move on to investigate the Calculus 3 version of what we have previously called the extreme value theorem. So stay tuned and take care.